Greetings and welcome to my new calculus channel. My name is John Gabriel. So in the previous lesson, which was lesson 5, we saw the meaning of division. In other words, what I explained to you in this lesson is that division is all about measure. So for example, if we write P over Q like this, okay, P over Q is equal to P divided by Q like that. Essentially nothing happens here because the P just goes to the top and the Q to the bottom. But then you'll say, oh, wait a minute, what about something like 20 over 6? Well, in this case, you're not really doing anything in terms of this definition, because this refers to ratios of magnitudes, okay? Ratios of magnitudes. I'm not going to type that out, but ratios of magnitudes. And this here refers to numbers. Okay, so this is an algebraic measure using the abstract unit. So when you write down 20 over 6, you're thinking about a number and you're measuring it using 6 as a unit. You don't have to measure it using 6 as a unit. You can measure it using, let's say, 5 as a unit, okay? 5. And that would be 5 plus 5 plus 5 plus 5, okay? In other words, 4 times, right? Make sense? Okay, so that's what we were looking at in the previous lesson. So this division here refers to ratios of magnitudes. This here refers to proper fraction. It refers to fractions, not proper, just fractions, which are numbers, by the way. And it can be measured in many different ways. So in this lesson today, we're going to look at more on fractions, okay? Now, we saw that when we divide or multiply, we use the same method, okay? What is that method? We add the numerators and denominators of a fraction so that the result remains proportional to the original. So for example, I showed you the case of 2 times 3 and 3 times 2. And of course, you get the same answer in both cases. And in this example here, I showed you that rather than using this long, tedious method, we could use equivalent fractions simply by multiplying the numerator by 3 and the denominator by 3 and get whole numbers, in which case we can get the answer faster. And this is really why it helps to memorize the multiplication tables up to 12 so that we can avoid this repeated addition of book 5 and proposition 12. Or subtraction. It's addition or subtraction because addition is defined in terms of subtraction. So what I'm telling you here is that learning the tables should come way after the basic theory is established. In other words, you need to know all these things long before you even get to the abstract unit. And so, for example, if you wanted to convert 3/7 and 5/4, we simply multiply the first by 4 over 4 and the second by 7 over 7, resulting in 12 over 28 and 35 over 28. So the same method means that we use denominators, which are the same, and that makes multiplying and dividing very easy. Okay. Now, what about simplifying fractions? So we saw an example of the fraction 5 over 4 where the numerator is greater than the denominator. So what's happening here is that you're seeing a whole part relationship where you're measuring using whole units and parts of the unit. But that's what you're doing anyway, because that's what 5/4 means. Okay, it means 4/4 plus 1/4, right? So calling this an improper fraction or even a mixed number by writing it as 1 1/4 without the plus sign is stupid. Okay, it's just confusing. It doesn't help in the pedagogy process or in the teaching of these concepts. The next thing we need to look at is the proper fraction, which is still used today. It's really a garbage concept. it means that the fraction lies between -1 and 1. And it's an inappropriate and confusing name, inappropriate, that suggests other fractions may not be valid. So where did it come from? Probably the product of some idiotic math research in the 16th or 17th centuries in England somewhere, because arithmetic manuals classified fractions as proper, improper, and compound. I'll get to what compound means in a moment. But there was no need to classify fractions because every number is a fraction without any exception. If if a number is not a fraction, it's not a number. Okay. So what is an improper fraction? An improper fraction is one where the numerator is greater in the mainstream. Of course, another garbage concept because this implies that fractions such as the natural numbers and also anything in the form of pk over k. For example, 6 over 3 is an improper fraction. That's bullshit. 6 over 3 is 2. So 2, 2 is an improper fraction. Do you see how this stupidity stuck and these things remained unchanged? So what did compound mean? So compound meant a fraction whose numerator or denominator is a fraction. Well, that's nonsense because a fraction consists of numbers. The numerator and the denominator are themselves numbers, as I showed you in the third lesson of this series, how we get number. So it's totally absurd and it's dropped out of usage because probably they finally figured out they were stupid and they don't use it any longer. Then the mixed fraction came along, and this was explained also earlier, where you were confronted with what division means. Okay, division means measure and vice versa. So the mixed concept was driven by the whole part approach, which we've seen fail consistently in pedagogy. And all numbers are expressed in terms of measures of the abstract unit, or measures using the abstract unit. So abandoning the Greek measure approach resulted much later in catastrophic garbage in mainstream mathematics, pure mathematics, called measure theory. If you do an undergrad math degree, you'll find out about that bullshit. It's truly ultra garbage. Now, this little diagram that you have on the side here arose from all these confusing and chaotic concepts. This just goes to prove that these people didn't understand the concept of number. So if you look at this here, I mean, all numbers are fractions. First of all, there are no irrational, real, complex, or imaginary numbers. These four here are not numbers. The only numbers are these, okay? Integers, natural, and rational. These are not numbers. So you may turn around and say, oh, what about the square root of 2? Well, the square root of 2 is realized from the failed measure of the ratio of the diagonal of the square to its side. Okay, that's all that the square root of 2 is. It's not a number. Even pi itself is not a number. So those are all misconceptions that arose from the confusion that started around the 16th or 17th century. Now, quick multiplication. For example, I bet you've seen this before, where you multiply two fractions and you just take the product of the numerators and the product of the denominators, and then you get PR over QS, right? Well, we know from the definition that P over Q times R over S is equal to P over Q divided by S over R. Remember, multiplication is division. It's reciprocal division. Okay, it's just flipping these two around. It's saying rather than measure with the second operand, take its reciprocal and measure it that way. So let's just quickly, no, I didn't mean to do that. Let's quickly do an example on that. So close that, come up. So if we have this here, let's do an example. So if we say 2 divided by 1 over 3, right? That's the same as 2 times 3. But if we had to say, if we had to measure 2 using 3, In other words, if we had to say 2 divided by 3, the answer would be 2/3, right? But now we're not going to divide by 3, we're going to divide by its reciprocal, which is the third. And you need 6 of those to measure 2, right? You need 6/3 to measure 2, all right? So that's what multiplication means. It's a reciprocal division measure. Therefore, if we take this here and we rewrite it as PR over QR, and we can do this first part here because we can multiply a fraction as we saw earlier by any number R, and then we divide that again also by SR times Q over Q, then we end up with this expression here, okay? And then again, we can multiply this whole expression by Q over QR, resulting in PR over QS. So we can do quick multiplication. And I bet you've never thought of that and you've wondered why you can do it. Now you know why. And from that, we can also do quick division, okay? Because division is what multiplication is defined in terms. So if we see something like 7 over 12 and 21 over 24, we can just change the operator and flip the two around. And this is much simpler than using the geoarithmetic operations of difference and sum as we learned earlier. However, if we're just simply dividing or multiplying using ratios of magnitudes, it's just a case of taking the antecedent of the first operand as the numerator and the consequent, and the antecedent of the second operand as the consequent of the quotient, which is going to be the result. So I've given you a lot in this video, a lot to think about. You have to basically go over these things very slowly, think about them, and in the next lesson, what we'll be covering is how we define a fraction in terms of the abstract unit. Now, this is how it's used in algebra, in the measurement in algebra. And of course, it's a pity that modern Greeks failed dismally to define the arithmetic names for numerator and denominator. And what I'm going to do is show you in the final lesson how in the final two lessons, 7 and 8, how they failed, okay? And a bit of history that led up to that point and why there is so much confusion still prevailing. Anyway, I hope you've enjoyed this video and that you'll join me again for the last two, 7 and 8, lesson 7 and 8. Become a subscriber, click like, follow me on Academia.edu, tell your friends about this channel so that I can earn a little bit more money. And that's pretty much it. I'm John Gabriel. Till next time, goodbye.